Hello, I'm Dr. Chris Parker, and today I'm going to introduce to you the basic statistics that designers need to deal with the kind of numbers that user testing brings up, the kind of data that will tell us if designs are better, and we can go to management and say, this is why you should follow this design. Now, we're going to do this by covering the basic concepts of statistics, and then in the next video, I'm going to go over all of the kinds of analysis that you may run. So don't worry, we're not going to analyze any data right now. So the way that we're going to cover the basics are thinking about what are statistics. It's a word we hear a lot, but we might not fully understand. What are descriptives? How do we describe data? What is the distribution of data? So what does an average even mean? And then how do we tell if two groups of scores are different with between groups differences? So let's start at the very beginning. What are statistics? Statistics are things that we see all the time. I took this off the BBC News website the other day, and this is describing coronavirus in the UK. We will be used to seeing these kind of charts and plots, and we might not actually understand what they are. We might not get them. We know they're important and we're showing them, but how can we actually understand them for ourselves without relying on the journalist to do the work for us? Now, the chances are when you're in school and you did maths, it made your head hurt and you felt like this. You probably thought, I can't do this, I can't do mental arithmetic, I can't do any of this stuff. Now, don't worry, you're not going to feel like that today. I'm going to try and teach you all the stats you need without using numbers, or at least as few numbers as I can get away with. Now, I was saying, which is you can drive a car without being a mechanic, so you can do statistics without knowing maths. I personally have published conference papers and journal papers in very high-ranking journals running statistics. I didn't know my times tables, and that's part of my dyslexia. I never learned them, and I got to use calculator for all kinds of mental maths. So if I can do this, you can too. So why do we designers have statistics? Now, designers almost always use simple statistics. So we talk about averages of this design, or if design 2 and 1 have different scores, very basic things. So we're not going to have to do anything hard. And if you get what I'm talking about in this video and you're following along, you will do absolutely fine. To achieve this, we only need simple software. So Excel and online calculators are your best friends. Now, you might go further and start using software called SPSS, maybe something like R or SAS, but that's unlikely. You can get by on everything you need as a designer using just Excel and simple online calculators, which is why we're going to focus on that today. But we do have to take some points to consider. So, what is a statistic? Well, these are things that help us filter how we see the world. Statistics focus our vision to understand what is really happening and prevent us from making incorrect assumptions over time. Now, what kind of thing is that? So you've got issues like gender inequality and gender bias. Now, you might work in a company which has a fantastic equality scheme, and there's no pay gap or anything. Men and women are paid the same and treated the same. You might work with lots of men and lots of women, and you don't see the inequality. That's because you can only see what you can see. You don't see the other companies. You don't see the other countries or maybe different parts of your company. When you use statistics and you take a more broad approach and collect data from a wider range, you can actually answer questions of, are these two groups different? And by how much? Can I prove it? As I said before, designers need not actually understand how to calculate statistics in order to understand the concepts. The hardest part of statistics is understanding what we're trying to achieve, the concepts, and that's what we're focusing on here today. Now, when we take it further, most events in life don't have an average. So we always talk about like the average number of this, the average score, the average speed, whatever. You know, if we took all the cars on the motorway and we recorded their speed, the average speed might be 73. But how many of those cars are actually driving 73? They're not. We're talking about a range. So we really talk about, most cars are going between this score and that score. Now, when we do statistics, generally it's talking about average things, but they're not really real. So what you're talking about in most stats is not about this average being higher than that average. It's about, are two groups of people significantly different? Are they overlapping? So I'll give you an example of that. Now, you might have average speed of the cars in France are going 75 miles an hour. Or maybe the average speed in the UK is going 73 miles an hour. But we take the ranges, and the ranges overlap so much that when you take any car going at any speed, it could be in most either countries. This will make sense a lot more very soon. But bear in mind, it's about ranges and overlapping ranges more than absolute averages. So let's take it from a very simple step. Let's talk about descriptives. Descriptives are in two main categories we can think about, which are frequencies and charts. Frequencies is just how many. So how many people, how many times it occur, how many groups. So example here, when using a fashion website to find a wedding outfit, men make 5 mistakes and women make 3 mistakes on average. Okay, so we are talking about the average bit here because we're not doing statistics, we're doing descriptives. So just simple numbers. So frequencies you use all the time. The next one is charts. I'm not going to go over all the kinds of charts. You probably know them by now. The pie chart, the line chart, the bar chart. Charts are just pictures, visualize data. Visualizing data lets the viewer infer similarities and differences between datasets and information. Simple charts are often better than complicated charts because a simple chart you look at and understand clearly. And charts, again, show averages, just that average number. So we've got, or in this case of the picture, it shows counts, frequencies. So this is how many false or misleading claims Donald Trump is making over his presidency. So we can look at this, and generally both groups are rising. He's making more false or misleading or false statements. But we can see that the amount of outright lies that he's made since January 2017 are increasing slightly, but not too much. He's maybe doubled his lies, but he's consistent at it. But the amount of false or misleading statements that aren't necessarily false, but they are pushing in a direction which isn't really happening, that's increasing. So he's just making a lot more stuff up and spinning a lot more stuff. So a simple chart can let you understand frequencies and how they relate to each other better. So far, we've not done anything that you wouldn't do at GCSE, just frequencies and charts. These take the averages, plot them out there, and you're good to go. That's not really statistics. So let's take a dive into what I mean by statistics and ranges of scores. We start with something called normal distribution, and then we're going to go on to something called standard deviation. Normal curve is your normal distribution. So it's a bell curve or normal curve. It's got a few different names. They all mean the same thing, which is this image here. And it's how common traits are distributed in a curve or bell shape. So the classic one is weight. Now, how many people are what weight category? Well, you're going to get some people, a very small amount of people, who are anorexic, and they're down the bottom. Then you get a very small people who are incredibly obese. And you're going to have lots of people in the middle who are kind of, I'm going to say average weight. When you think of what a person looks like, the amount of body fat and pieces, that's what I mean, that part in the middle. So have lots of people that size. So the normal curve, just the distribution of how many people fit into each category, that underlines almost all statistical analysis. So I'm going to give you two examples. The first one is, imagine we've got 10 people in a room and they flick a coin 10 times each. Go over to a chart and it's got the amount of heads that have been flipped written at the bottom, and they just put a cross over the number which represents what they got. So in this example, we had quite a few people say, well, I had 4 heads. A lot of people saying 5 and 6. Quite a few people said 7 heads. The same number of people said 8 heads as said 4 heads. No one flipped a coin and got 1, 2, 3, 9 or 10. So we repeat this and do 10 flips, walk up to there, put a cross over how many heads you got. And eventually you're going to get a normal curve appearing where lots and lots of people flipped 5 or 6 heads on a coin. A few people had 1 or 10, but they're the extreme outliers. So what this does is the normal curve describes the probability of getting ahead when flipping a coin. So at the very low end, low probability, very high end, low probability, in the middle, high probability. We see normal curves everywhere when we look at data. Here's one which I showed you earlier, which is the coronavirus infected cases. How many recorded cases we got? We see that it went sharply up, stabilized, and went down. Notice that this curve is not equal. Normal curves might form a clear equal-sided bell curve. They rarely do. Quite often it is jagged. And we'll see here to the right that we're on another curve here. This is after lockdown's finished, people are going to the pub again, going to restaurants, they're seeing their friends, and they're infecting each other. So the cases are rising. We've also got more testing, which does make a difference about the scores. So we can't completely compare where we are in September versus where we were in April. Even though the numbers are equal, the conditions have changed. But anyway, the point is we see bell curves forming, and we will see bell curves forming with coronavirus in waves, possibly forever. So that is what a bell curve is. It's just the curve that data relies on. Standard deviation is the next topic we want to talk about. Now, as I said before, no person is average, no event is average. But what we have is a range of scores that are very common. So, a standard deviation is a measure of that range. Now, one standard deviation describes the range above or below the average. And we take it, one standard deviation is about 34%. And so take that as 2 standard deviations, describes the below and the above. Together, we get 68% of everyone is captured within 1 standard deviation. In this picture, it's the dark blue, and the average is in the middle. So the average person might be that line. Very few people are average that score. But we can say that most people fit into 68%. Most people are somewhere in that blue. Let's take an example to make this a bit clearer. So we've got a basketball team, and a designer measures the height of the team. The average height, total height divided by number of people, that is 183 centimeters. The standard deviation is 15 centimeters. So the average player, so 68% of players that would be in the team, will be between 168 and 193 centimeters. We have a range. They're all tall. This is a normal basketball team, and they recruit based on talent. Then we go to another team. So a designer is measuring the height of a basketball team. And the average height, again, is 183 centimeters, but the standard deviation this time is 0. So every single member of that team is 183 centimeters tall. This is a very strange basketball team because they are recruiting on height and not recruiting on talent. So standard deviation is just describing how wide that range is. You might have a sample with a wide standard deviation because people have a lot of varying scores. You might have a sample with a very small standard deviation because everyone's scores are very close together and don't change much. So we can imagine that. We have normal curves of probability and we have standard deviation of how wide. Let's see how this is used in statistics. We have a thing called between differences. And we are going to use this to answer some very simple questions, which we are going to have as designers. We're going to be asking, are my groups different? No, I give men something and I do a test and get a score. I give women something and do a test and get a score. Are their scores actually different because we've got a wide range of numbers? How big is the difference between my groups? And what is the probability that my results are actually correct? And we're going to answer those 3 questions with basic concepts. So the first one is significance. Significance tells you if groups are different. So we've got 2 normal curves and they overlap a lot. So there is a high probability that if you score where that red line is, you could be in the green or the pink group because there's such a high overlap of those. But we take this other one where we've got 2 groups, but they have a very low overlap. If you score that red line, it's almost certain that you are in the green group. It's very hard for you to be in the pink group and score that high. So, the higher the overlap, the lower the chance of groups being different. And most statistics are all about, are groups different? Now, very rarely do you get a data set where the groups are very far apart. There's always some degree of overlap, and it can be very hard to tell if there is higher overlap or low overlap just by looking at the average scores, which is why we need the significance value. Significance is the probability that 2 groups are different. Now, something really, really important here. Significance only tells you if they're different. It doesn't tell you anything about the size of the difference. So, you hear people going, oh, it's a very significant test, very significant, high significance. Who cares? And this is why. In maths, you measure, or you have this benchmark significance called the alpha. You will have done this in school. So the alpha is normally 0.05. So if you score significance lower than 0.05, you are significant, the groups are different, carry on. Now what the alpha means is the probability that you made a mistake, or what's the certainty that we're right. So an alpha of 0.05 means there is 95% chance of being right. How confident? If we add a alpha of 0.01, you are 99% certain that you are correct, that there is a difference. We can go on like that. Now, you normally take an alpha of 0.05. So when a designer runs a test, use 0.05, you score a significance of 0.04. 0.04 is less than 0.05, so your test is significant. Hooray! If you ran another test and your significance was 0.01, that does not mean your groups are bigger. It just means that in the second test, you have more confidence that the test is correct, but both tests pass your basic level, so both ones are equal. They just tell you there's difference, nothing else. Let's have an example. So a designer collects lots of performance data about how long people take to use 3 websites. So we've got design A, B, and C with some times there and standard deviations. Don't worry about the numbers. The significance, so design A and design B were significantly different at 0.04. It's below 0.05, we're good. Design C or should be design B and design C is significant at 0.01. Well, that's definitely lower than 0.05, so we're good again. But we're only telling here that there is difference. We do not know how big the difference is. It doesn't mean that design B and C, second test, is somehow better. It's just we have more confidence that it's correct. So how do we tell how big the differences is between groups? We need a measure called effect size. All it is saying how big the difference is. It goes on a scale between 0 and 1. So significance tells us 2 groups are different. Effect size tells us the size of that difference. So let's have a look here. We've got lots of overlap on the first area, so low effect size. We have hardly any overlap here, so a large effect size. But let's visualize this in a better way. Kids of the same age have a small effect size on height, and kids of different age have a large effect size on their height. And that's what it is. When we know there's significance, we then look for the effect size to see, is this something we should be excited about? Generally, they come in small, medium, or large differences. You want a medium or large. We'll come on to that later. The third area is power. What's the probability that my results are correct? Now, we did start with the alpha, 0.05, saying if you're lower than 0.05, that will tell you the probability that our answer is right, that there is a difference. But what if the whole thing is wrong? What if there's something wrong with the data? Now, to answer that question, we've got to understand what errors are, what mistakes are. So, there's 2 kinds of error we can have. There's a type 1 error, which is achieving a non-significant outcome, but in reality, out there in the world, there are significant differences. So, remember, a woman who's heavily pregnant being told by a doctor that she's not pregnant. That is a type 1 error. If you got a false negative, you can have a false positive, which is a type 2 error. So achieving a significant outcome, but in reality, both those normal curves will overlap a lot. So think of a doctor telling a man that he is pregnant. Again, crazy, it's an error, it's a type 2 error. Power is this wonderful concept that many people get wrong, but once you understand it, it is magical. Designers can run a test called power calculations. Power calculations describe the probability that the whole thing you're doing, all your results, are correct. Now, generally, you want to have an 80% benchmark, which is 0.8. That if you get 0.8 or above, we can say this test is good. We like this. So 80% chance of correct, 20% chance of a type 2 error. Now, if your power was 30%, which is 0.3, then there's 70% chance that all calculations are wrong. We're going to come back to this later on. Don't worry too much. So let's think about multiple comparisons and false positives. This is where things get really deep. So I'm going to go slowly and we're going to work through this together, and you'll see where the alpha comes into its role again. So the first part is just power. We need to get the power. The second part is make sure that alpha is right. So a designer tests if happiness increases when they show people a yellow picture. So we set alpha at 0.05. We test their happiness now, show them the picture, test happiness afterwards. We see a difference. Its significance score is below 0.05. So we have 95% probability that there is difference between groups. Great, we're happy with that. And we'll assume we've got a power above 0.8. What happens if we run 4 tests? Well, there is an 18.5 probability that one of those tests is wrong. Because I'll go into the maths behind it. Below is a simple formula for the probability of a false positive, but the more tests you do, the probability that your tests are wrong increases. Let's have a look at that on a large scale. So if you run 13 or 14 tests, you have a 50% chance that one of those tests is a false positive, type 2 error. If you run 27 tests, you have a 75% chance that one of your results is a type 2 error. You haven't done anything wrong, you collected enough data, it's got lots of power, it's just that little bit, 5%, they multiply up, and the probability is eventually. So you might never reach that 100% chance, but we'll get to the point where it's pretty damn likely that one of your results is wrong. So we can fix this, and we've got a concept called a Bonferroni correction. A Bonferroni correction is where you take the original alpha, divide it by the number of tests that you are doing. So if we have original alpha of 0.05, 14 tests, 0.05 divided by 14 equals 0.004. 0.004 becomes our new alpha for all of those 14 tests. You might get lots of tests where you show people a colour and see if it makes them happier, and you have a significant difference between the groups, and that significance is 0.01. Now, 0.01 is definitely lower than 0.05, our original alpha, but it's not smaller than a Bonferroni correction of 0.004. So what we do is we ignore every significant test above 0.004, meaning that out of all the 14 tests, we still only have the 5% chance of type 2 error. So, gone quite far, gone quite deep. So what have we done? We have talked about what are statistics. We've talked about descriptives with frequencies and counts and pie charts and bar charts. We've talked about normal distribution, normal curves and bell curves. We talked about between groups differences. And we've talked about how you can tell if your answer is right using the alpha, using significance, standard deviations. You can tell if you've got enough power. And all you need to know right now is the concept of your power must be 0.8 or above. In the next video, we're going to go forward and actually calculate all of these items. And we're going to take it slowly, piece by piece, and very soon you're going to see how all these concepts, which might be a bit abstract, are going to start to come together and make sense and help you work more effectively as a designer.